Hello, everyone. My name is Edward Jin, and welcome to Lab 2, Magnetic Field of a Bar Magnet for Physics 2212. In this experiment, we explored the magnetic field of a bar magnet and how it changes with distance. Some objectives are we wanted to characterize the magnetic field produced by the bar magnet, apply the Biot-Savart law to quantify the field both on axis and at various off-axis angles, and then build and run a GlowScript simulation to model these fields. And then here are some of the key findings. We saw that as the magnetometer approach the magnet, the X component reading rises and field strength grows with decreased separation. Here are some core concepts. The Savart relationship describes how a tiny moving charge or differential current segment generates a magnetic field at some observation point. Magnetic field of a dipole. A magnetic dipole is described as a closed circulation of an electric current system. And then distance dependence formula, where the magnitude of a magnetic field due to a bar magnet will fall off with distance. And then here is the experimental procedures. We start by zeroing the magnetometer with the aid of the bar magnet, a ruler, and tape for consistent alignment. Then we take field readings at multiple marked separations using using those values to establish the distance versus V relationship. And then we code a model off the on-axis and off-axis of our expressions. And then here the model system and surroundings. The system would be the phone and the magnetometer, and then the surroundings would be the earth and the magnet. So here in the the measured experiment, after the collecting the data, I used Excel to plot a magnetic field strength against distance. From the trend line, we saw a logarithmic decay as expected. Excel also calculated the average net magnetic field, which came out to be about 7.2 times 10 to the negative 5 Teslas. And so next came the coding portion in GlowScript. Here I programmed the equations for a magnetic field due to a dipole to calculate the expected values for both on-axis and off-axis positions. GlowScript also let me visualize the field with arrows showing direction and strength at different points in space. As noted here, as you could see, the magnitude of B at 45 degrees was equal to 4.18 times 10 to the negative 5. This simulation produced a vector field at a 45-degree angle and a distance d, where the x component was approximately 1.3 times 10 to the negative 5, and the y component was 3.9 times 10 to the negative 5, and this ended up giving us our magnitude. By taking the magnitude of the vector, we had the theoretical magnetic field of strength of about 4.18 times 10 to the negative 5 Teslas. And I just want to note that this is much smaller than the 7.2 times 10 to the negative 5 that was measured in the experimental process. So there obviously are going to be some potential sources of error here. And so, what caused some of these discrepancies? We could say a few things. The magnetometer app on the phone maybe didn't perfectly, have good accuracy and might have changed some of the numbers up a little bit. Nearby electronics or magnetic materials could have interfered as well. Errors may have occurred during the process of measuring distances, which could have also led to a difference in results. Misalignments of the bar could have affected the field orientation and strength readings. The observed gap between the expected and actual values was likely due to a mix of all of these contributing factors. And so, what if? Firstly, in this case, the measured magnetic field would change in both the x and y components, since magnetic north would influence both directions more equally. However, the z component would remain unchanged, and this is because the magnetometer was still placed on a surface level. And then for the second what if, even though the magnets are combined, they still point in the same direction, so overall magnetic behavior remains consistent, and the key difference is strength. The field becomes more powerful, similar to replacing the original bar magnet with a strong